Hey, welcome back. And in this lecture, we will talk about Gomery cuts. All right. So, what's the picture so far? The overall idea is we have a problem in this slack form where we have added slack variables. We ensure that the matrices A, vectors B and C are integers, and therefore we can also claim that the slack variables that we added should also be integral. Okay. And therefore, now we would like to solve the LP relaxation of this problem using the simplex algorithm. And we start with the LP relaxation, okay, where we drop these two constraints that the variable and the slack are integral. And we start with the initialization phase, go through the optimization phase, and end up with the final dictionary. One thing I have to warn you that confuses many people is that we start off with an integral problem, an integral dictionary, but when we get to the final dictionary, this dictionary does not have to be an integral dictionary. I hope that part is clear. Okay, we just solve it as we would solve any simplex problem, and you have enough experience by now that you know what to expect in this final dictionary. All right, so skipping through everything, let's just look at the final dictionary, which is right here. Okay, it has non-basic variables xn and basic variables xp. The solution to the basic variables is given by b tilde, and c and tilde is the objective row coefficients, a tilde being the matrix of the dictionary. All of this I hope is clear. Now let's examine b tilde. Now, if all entries here are integers, then the optimal solution to ILP has been found. We can now leave because we are done. Okay, why is that? Because xb will be assigned to all integer variables in b tilde, integer values in b tilde, excuse me, and xn will be assigned to 0, which are all integers. Therefore, the optimal solution to the ILP is found. On the other hand, if B tilde has fractional entries, we are going to now derive a cutting plane by looking at this final dictionary. The cutting plane is going to come up. Let us see how that works. Here is an example where I directly jump to the final dictionary. The starting parts of the example are not important to me. Let us directly jump into the final dictionary. We will do a complete example from start to finish in the next lecture. Okay, now this dictionary has non-integral values for 1.2 for x1 and 2.5 for x6. And remember, the way we have set up this problem, all variables, original problem variable and slack variables, are all necessarily integral. That's the way we set it up. So we know that x1 should be an integer and x6 should be an integer, but in this final dictionary, they aren't. Okay, so how do we fix this? The way to fix this is to first identify a row which is fractional. So here x1 is fractional, x6 is fractional, and since we bothered making the objective function also integral, we also know that z should be an integer, and here z is fractional. Okay, but we will deal with that later. So we can now first identify a row with a fractional constant. You can either identify x1, x6, or you can even identify z, but we will leave that alone for a second to avoid confusion. Now let's examine the row in detail. So x1, I've just rewritten this row is 1.2 minus 3.1 x2 plus 4.3 x3 minus 0.5 x5. Let's take this row and let's rearrange things. Okay, let's move all the variables to one side and keep the constant to the other. I hope this part does not pose any challenges. We've just rearranged this. So minus 3.1 becomes plus 3.1, plus 4.3 becomes minus 4.3, and minus 0.5 becomes plus 0.5. That's it. Just rearranged. So far, so good. All right. So we can identify any of the rows. We identified x1 in this example. You could have identified x6 or z, and I will repeat that again. All right. Now, I'm going to split this expression on the left into two expressions. One that I know to be an integer, and the other which will have to carry any fractional part. So here I split it into x1 plus 3x2 minus 5x3, and I'll tell you why minus 5 in a second, plus 0x5. I'm just taking the floor of these numbers. So floor of 1 is 1, floor of 3.1 is 3, floor of minus 4.3 is minus 5. Remember, floor is the smallest integer less than or equal to, and floor of 0.5 is 0. And this part, I call this to be A. And then the remainder, 0.1x2, 0.3x3, 0.7x3, because I put in a minus 5, so I have to put plus 0.7, and plus 0.5x5 must be B. and I say whatever values a and b take, a plus b must be 1.2. So it's 1 plus zero point 0.2. Okay, so this is the key step in deriving the cutting plane. We note that a must be an integer because x1, x2, x3 and x5 are integers and the coefficients are integers. So a is an integer. B must be an integer plus a fraction because it has zero point 0.1 x2, imagine x2 to be 11, so this would be 1.1, 0.7 x3, imagine x3 to be 15, this would be 10.5, 0.5 x5, imagine x5 to be 5, this would be 2.5. So the addition is going to give us an integer plus a fraction. And one more magic that happens because of the way we set it up is we note that these coefficients that come out here are non-negative or positive coefficients, 0.1, 0.7 and 0.5. Therefore, since x2 is greater than equal to 0, x3 greater than equal to 0, x5 greater than equal to 0, b itself is greater than or equal to 0. Okay, and the last fact is a plus b is 1.2. Okay, a is integer, b is an integer plus some fraction between 0 and 1, okay, and b greater than equal to 0. With all these facts, I now want to think more about what can b be. All right, let's see this in more detail. So here I have summarized all the 4 facts. A is an integer, b has a fractional part, b greater than equal to 0, a plus b is 1.2. Okay, now let's look at all the possibilities that A and B can be. So A can be 1, B can be 0.2. As you imagine, A is 1, B is 0.2. It's very tempting to say that this is the only possibility, but note that there are many other possibilities. Okay, for example, A can be minus 3 and B can be 4.2 because there's a minus 5x3. We don't say that A is positive. A may be positive, negative, 0. We do not know. So A can be minus 3, B can be 4.2. A can be minus 100, B can be 101.2. That's all possible. Okay. What's not possible? Can A be 2 and B be minus 0.8? No, that cannot be possible because B greater than equal to 0. Can A be 1.1 and B be 0.1? That's not possible because A is an integer. Can A be 4 and B be minus 2.8? Again, you know it's not possible because B greater than equal to 0. So if you look at all the possibilities, the things that are shaded blue, one fact jumps out at you. And the fact is that the fractional part of B is 0.2. B is 0.2, it can be 1.2, it can be 2.2, 3.2, 101.2, 4.2, but it has to be something 0.2. Okay, and B greater than equal to 0 now naturally becomes B greater than equal to 0.2. Okay, we can say something better. B is greater than equal to 0.2. This is the key fact behind the derivation of the cutting plane that you have to convince yourself. If you're convinced of this, the rest of this is really easy. Okay, so if you're not convinced, I suggest that you rewind and go through this argument again and convince yourself that the fractional part of B is some whole number plus 0.2. Okay, it's positive. Okay, so B must be greater than equal to 0.2. It cannot be between 0 and 0.2. Okay, it has to be 0.2, 1.2, 2.2, 3.2, something plus 0.2, where the something is greater than equal to 0. So B itself is greater than equal to 0.2. In other words, B minus 0.2 is an integer and B greater than equal to 0.2. This part will give us now our cutting plane. All right, okay, if that part is clear, then here we go. The cutting plane is simply going to be B, okay, which is going to be, if you go back 2 slides or just 1 slide, okay, B is 0.1 x2 plus 0.7 x3 plus 0.5 x5, okay, so B greater than equal to 0.2, 0.1 x2 plus 0.7 x3 plus 0.5 x5. This part is B greater than equal to 0.2. That is the cutting plane that we need, and I'll show you why this cutting plane works. I hope this part is clear. This is the key part behind the derivation of the cutting plane, the thing that we need to understand before we can completely move on. How does this work in general? Just the same way I described to you in the example. You first choose a row for which the constant bk is not an integer, and you do this in the final dictionary of the LP relaxation. You now choose the equation of the cutting plane given by the fractional part of minus ak1, not plus ak1 because we move it to the other side to derive the cutting plane, minus plus the fractional part of minus ak2 da 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 plus the fractional part of minus akn multiplied by xi1, xi2, xin greater than equal to the fractional part of bk. This is exactly the same thing that we derived in the previous example. Okay, so if you look at this, what you get is the fractional part of b becomes the right hand side. The fractional part of minus 3.1 is plus 3.1, which is 0.1. The fractional part of minus 4.3 is 0.7, and the fractional part of minus 0.5, which is plus zero point 0.5, is 0.5. So that gives us the cutting plane. I hope that is clear. Now you may ask me, what's the formal definition of this fractional part? It's just x minus the floor of x. Okay, I hope this part is clear. This formalizes the cutting plane as we know it, and this is called the Gomery-Schwartz cut. It's a very important definition, and once we have this cutting plane, we can add it back to the problem and proceed with solving the problem recursively. All right, so let us now prove that the cutting plane does not have any integers. All the integer solutions to the original problem will continue to satisfy the cutting plane. How do we prove this? So here we go again with the cutting plane, okay? And the claim is every integer feasible point of the original ILP continues to satisfy the cutting plane constraint, which means we don't lose any integer point in this process. Okay? And therefore, here we go. So what we have is we can now derive the cutting plane, and we can guarantee ourselves that the cutting plane is going to be, in fact, satisfy all the integer points of the original problem are going to satisfy the cutting plane. It's not going to lose any integer point, but it could lose some rational points. Some fractional, some solutions of the LP relaxation are lost, and that is totally fine. Okay, so let us go back to this example. We initially chose x1 to derive a cutting plane. What happens if we chose x6 instead? The cutting plane we get would be 0.7 x2, because this is plus 1.3 here. We take the fractional part of minus 1.3, which is 0.7. We take the fractional part of 2.1. Here it's minus 2.1. We take the fractional part of plus 2.1, which is 0.1. And the fractional part here is taken of minus 1, which is 0. So you get 0.7 x2 plus 0.1 x3 plus 0 x5 greater than equal to the fractional part of 2.5, which is 0.5. I hope this is clear. Okay, and let's now do the objective row. Because we bothered in the original ILP setup, the standard form, to also make the objective an integer, we can use a cutting plane from the objective row as well. The objective row gives us the cutting plane 0.2 x2 minus 1.2 is transformed to plus 1.2, and its fractional part is 0.2. Similarly, 0.3 x3 plus 0.1 x5 greater than or equal to 0.7. Okay, and therefore we can derive cutting planes by looking at every row in the dictionary which has a fractional constant entry. We can use that to derive a cutting plane. Okay, so what remains? What remains is updating the dictionary and setting up for subsequent iterations, which we will cover in the very next video. Thank you.